Electrostatics, Chapter 1, Description of Phenomena, Electrification by Friction. Experiment 1. Let a piece of glass and a piece of resin, neither of which exhibits any electrical properties, be rubbed together and left with the rubbed surfaces in contact. They will still exhibit no electrical properties. Let them be separated. They will now attract each other. If a second piece of glass be rubbed with a second piece of resin, and if the pieces be then separated and suspended in the neighborhood of the former pieces of glass and resin, it may be observed, first, that the two pieces of glass repel each other. Second, that each piece of glass attracts each piece of resin. Third, that the two pieces of resin repel each other. These phenomena of attraction and repulsion are called electrical phenomena, and the bodies which exhibit them are said to be electrified, or to be charged with electricity. Bodies may be electrified in many other ways, as well as by friction. The electrical properties of the two pieces of glass are similar to each other, but opposite to those of the two pieces of resin. The glass attracts what the resin repels, and repels what the resin attracts. If a body electrified in any manner whatever behaves as the glass does, that is, if it repels the glass and attracts the resin, the body is said to be vitreously electrified. And if it attracts the glass and repels the resin, it is said to be resinously electrified. All electrified bodies are found to be either vitreously or resinously electrified. It is the established practice of men of science to call the vitreous electrification positive and the resinous electrification negative. The exactly opposite properties of the two kinds of electrification justify us in indicating them by opposite signs. But the application of the positive sign to one rather than to the other kind must be considered as a matter of arbitrary convention, just as it is a matter of convention in mathematical diagrams to reckon positive distances towards the right hand. No force, either of attraction or of repulsion, can be observed between an electrified body and a body not electrified. When, in any case, bodies not previously electrified are observed to be acted on by an electrified body, it is because they have become electrified by induction. Electrification by induction. Experiment 2. Let a hollow vessel of metal be hung up by white silk threads, and let a similar thread be attached to the lid of the vessel so that the vessel may be opened or closed without touching it. Let the pieces of glass and resin be similarly suspended and electrified as before. Let the vessel be originally unelectrified. Then, if an electrified piece of glass is hung up within it by its thread without touching the vessel and the lid closed, the outside of the vessel will be found to be vitreously electrified, and it may be shown that the electrification outside of the vessel is exactly the same in whatever part of the interior space the glass is suspended. If the glass is now taken out of the vessel without touching it, the electrification of the glass will be the same as before it was put in, and that of the vessel will have disappeared. This electrification of the vessel, which depends on the glass being within it and which vanishes when the glass is removed, is called electrification by induction. Similar effects would be produced if the glass were suspended near the vessel on the outside. But in that case, we should find an electrification vitreous in one part of the outside of the vessel and resinous in another. When the glass is inside the vessel, the whole of the outside is vitreously, and the whole of the inside resinously electrified. Electrification by conduction. Experiment 3. Let the metal vessel be electrified by induction, as in the last experiment. Let a second metallic body be suspended by white silk threads near it, and let a metal wire, similarly suspended, be brought so as to touch simultaneously the electrified vessel and the second body. The second body will now be found to be vitreously electrified, and the vitreous electrification of the vessel will have diminished. The electrical condition has been transferred from the vessel to the second body by means of the wire. The wire is called a conductor of electricity, and the second body is said to be electrified by conduction. Conductors and insulators. Experiment 4. If a glass rod, a stick of resin or gutta percha, or a white silk thread had been used instead of the metal wire, no transfer of electricity would have taken place. Hence, these latter substances are called non-conductors of electricity. Non-conductors are used in electrical experiments to support electrified bodies without carrying off their electricity. They are then called insulators. The metals are good conductors. Air, glass, resins, gutta percha, vulcanite, paraffin, and so on are good insulators. But as we shall see afterwards, all substances resist the passage of electricity, and all substances allow it to pass, though in exceedingly different degrees. In experiment 5, the electrified vessel produced electrification in the second metallic body through the medium of the wire. Let us suppose the wire removed and the electrified piece of glass taken out of the vessel without touching it and removed to a sufficient distance. The second body will still exhibit vitreous electrification, but the vessel, when the glass is removed, will have resinous electrification. If we now bring the wire into contact with both bodies, conduction will take place along the wire, and all electrification will disappear from both bodies, showing that the electrification of the two bodies was equal and opposite. Experiment 5. In experiment 2, it was shown that if a piece of glass, electrified by rubbing it with resin, is hung up in an insulated metal vessel, the electrification observed outside does not depend on the position of the glass. If we now introduce the piece of resin with which the glass was rubbed into the same vessel without touching it or the vessel, it will be found that there is no electrification outside the vessel. From this, we conclude that the electrification of the resin is exactly equal and opposite to that of the glass. By putting in any number of bodies electrified in any way, it may be shown that the electrification of the outside of the vessel is that due to the algebraic sum of all the electrifications, those being reckoned negative, which are resinous. Experiment 6. Let a second insulated metallic vessel B be provided, and let the electrified piece of glass be put into the first vessel A, and the electrified piece of resin into the second vessel B. Let the two vessels be then put in communication by the same wire as in experiment 3. All signs of electrification will disappear. Next, let the wire be removed, and let the pieces of glass and of resin be taken out of the vessels without touching them. It will be found that A is electrified resinously and B vitreously. If now the glass and the vessel A be introduced together into a larger insulated vessel C, it will be found that there is no electrification outside. This shows that the electrification of A is exactly equal and opposite to that of the glass, and that of B may be shown in the same way to be equal and opposite to that of the piece of resin. We have thus obtained a method of charging a vessel with a quantity of electricity exactly equal and opposite to that of an electrified body without altering the electrification of the latter. And we may in this way charge any number of vessels with exactly equal quantities of electricity of either kind, which we may take for provisional units. Experiment 7. Let the vessel B, charged with a quantity of positive electricity, which we shall call for the present unity, be introduced into the larger insulated vessel C without touching it. It will produce a positive electrification on the outside of C. Now let B be made to touch the inside of C. No change of the external electrification will be observed. If B is now taken out of C without touching it and removed to a sufficient distance, it will be found that B is completely discharged, and that C has become charged with a unit of positive electricity. We have thus a method of transferring the charge of B to C. Let B be now recharged with a unit of electricity, introduced into C already charged, made to touch the inside of C, and removed. It will be found that B is again completely discharged, so that the charge of C is doubled. If this process is repeated, it will be found that however highly C is previously charged, and in whatever way B is charged, when B is first entirely enclosed in C, then made to touch C, and finally removed without touching C, the charge of B is completely transferred to C, and B is entirely free from electrification. This experiment indicates a method of charging a body with any number of units of electricity. We shall find, when we come to the mathematical theory of electricity, that the result of this experiment affords an accurate test of the truth of the theory. Before we proceed to the investigation of the law of electrical force, let us enumerate the facts we have already established. By placing any electrified system inside an insulated hollow conducting vessel and examining the resultant effect on the outside of the vessel, we ascertain the character of the total electrification of the system placed inside, without any communication of electricity between the different bodies of the system. The electrification of the outside of the vessel may be tested with great delicacy by putting it in communication with an electroscope. We may suppose the electroscope to consist of a strip of gold leaf hanging between two bodies charged, one positively and the other negatively. If the gold leaf becomes electrified, it will incline towards the body whose electrification is opposite to its own. By increasing the electrification of the two bodies and the delicacy of the suspension, an exceedingly small electrification of the gold leaf may be detected. When we come to describe electrometers and multipliers, we shall find that there are still more delicate methods of detecting electrification and of testing the accuracy of our theorems. But at present, we shall suppose the testing to be made by connecting the hollow vessel with a gold leaf electroscope. This method was used by Faraday in his very admirable demonstration of the laws of electrical phenomena. 34. The total electrification of a body or system of bodies remains always the same, except insofar as it receives electrification from or gives electrification to other bodies. In all electrical experiments, the electrification of bodies is found to change, but it is always found that this change is due to want of perfect insulation, and that as the means of insulation are improved, the loss of electrification becomes less. We may therefore assert that the electrification of a body placed in a perfectly insulating medium would remain perfectly constant. Second, when one body electrifies another by conduction, the total electrification of the two bodies remains the same. That is, the one loses as much positive or gains as much negative electrification as the other gains of positive or loses of negative electrification. For if the two bodies are enclosed in the hollow vessel, no change of the total electrification is observed. Third, when electrification is produced by friction or by any other known method, equal quantities of positive and negative electrification are produced. For the electrification of the whole system may be tested in the hollow vessel, or the process of electrification may be carried on within the vessel itself, and however intense the electrification of the parts of the system may be, the electrification of the whole, as indicated by the gold leaf electroscope, is invariably zero. The electrification of a body is therefore a physical quantity capable of measurement, and two or more electrifications can be combined experimentally with a result of the same kind as when two quantities are added algebraically. We therefore are entitled to use language fitted to deal with electrification as a quantity as well as a quality, and to speak of any electrified body as charged with a certain quantity of positive or negative electricity. Paragraph 35. While admitting electricity, as we have now done, to the rank of a physical quantity, we must not too hastily assume that it is or is not a substance, or that it is or is not a form of energy, or that it belongs to any known category of physical quantities. All that we have hitherto proved is that it cannot be created or annihilated, so that if the total quantity of electricity within a closed surface is increased or diminished, the increase or diminution must have passed in or out through the closed surface. This is true of matter, and is expressed by the equation known as the equation of continuity in hydrodynamics. It is not true of heat, for heat may be increased or diminished within a closed surface without passing in or out through the surface by the transformation of some other form of energy into heat, or of heat into some other form of energy. It is not true even of energy in general if we admit the immediate action of bodies at a distance. For a body outside the closed surface may make an exchange of energy with a body within the surface. But if all apparent action at a distance is the result of the action between the parts of an intervening medium, and if the nature of this action of the parts of the medium is clearly understood, then it is conceivable that in all cases of the increase or diminution of the energy within a closed surface, we may be able to trace the passage of the energy in or out through that surface. There is, however, another reason which warrants us in asserting that electricity, as a physical quantity synonymous with the total electrification of a body, is not, like heat, a form of energy. An electrified system has a certain amount of energy, and this energy can be calculated by multiplying the quantity of electricity in each of its parts by another physical quantity, called the potential of that part, and taking half the sum of the products. The quantities electricity and potential, when multiplied together, produce the quantity energy. It is impossible, therefore, that electricity is only one of the factors of energy, since the product electricity times potential is the energy. Energy, which is the product of these factors, may also be considered as the product of several other pairs of factors, such as a, a force multiplied by a distance through which the force is to act, a mass multiplied by gravitation acting through a certain height, a mass multiplied by half the square of its velocity, a pressure multiplied by a volume of fluid introduced into a vessel at that pressure, a chemical affinity multiplied by a chemical change measured by the number of electrochemical equivalents which enter into combination. If we obtain distinct mechanical ideas of the nature of electric potential, we may combine these with the idea of energy to determine the physical category in which electricity is to be placed. Paragraph 36. In most theories on the subject, electricity is treated as a substance, but inasmuch as there are two kinds of electrification which, being combined, annul each other, and since we cannot conceive of two substances annulling each other, a distinction has been drawn between free electricity and combined electricity. Theory of two fluids. In the theory called that of two fluids, all bodies, in their unelectrified state, are supposed to be charged with equal quantities of positive and negative electricity. These quantities are supposed to be so great that no process of electrification has ever yet deprived a body of all the electricity of either kind. The process of electrification, according to this theory, consists in taking a certain quantity P of positive electricity from the body A and communicating it to B, or in taking a quantity N of negative electricity from B and communicating it to A, or in some combination of these processes. The result will be that A will have P plus N units of negative electricity over and above its remaining positive electricity, which is supposed to be in a state of combination with an equal quantity of negative electricity. This quantity, P plus N, is called the free electricity. The rest is called the combined, latent, or fixed electricity. In most expositions of this theory, the two electricities are called fluids because they are capable of being transferred from one body to another and are, with thin conducting bodies, extremely mobile. The other properties of fluids, such as their inertia, weight, and elasticity, are not attributed to them by those who have used the theory for merely mathematical purposes. But the use of the word fluid has been apt to mislead the vulgar, including many men of science who are not natural philosophers, and who have seized on the word fluid as the only term in the statement of the theory which seemed intelligible to them. We shall see that the mathematical treatment of the subject has been greatly developed by writers who express themselves in terms of the two fluids theory. Their results, however, have been deduced entirely from data which can be proved by experiment, and which must therefore be true, whether we adopt the theory of two fluids or not. The experimental verification of the mathematical results, therefore, is no evidence for or against the peculiar doctrines of this theory. The introduction of two fluids permits us to consider the negative electrification of A and the positive electrification of B as the effect of any one of three different processes which would lead to the same result. We have already supposed it produced by the transfer of P units of positive electricity from A to B, together with the transfer of N units of negative electricity from B to A. But if P plus N units of positive electricity had been transferred from A to B, or if P plus N units of negative electricity had been transferred from B to A, the resulting free electricity on A and on B would have been the same as before, but the quantity of combined electricity in A would have been less in the second case and greater in the third than it was in the first. It would appear, therefore, according to this theory, that it is possible to alter not only the amount of free electricity in a body, but the amount of combined electricity. But no phenomena have ever been observed in electrified bodies which can be traced to the varying amount of their combined electricities. Hence, either the combined electricity has no observable properties, or the amount of the combined electricities is incapable of variation. The first of these alternatives presents no difficulty to the mere mathematician, who attributes no properties to the fluids except those of attraction and repulsion. For in this point of view, the two fluids simply annul one another, and their combination is a true mathematical zero. But to those who cannot use the word fluid without thinking of a substance, it is difficult to conceive that the combination of the two fluids shall have no properties at all, so that the addition of more or less of the combination to a body shall not in any way affect it, either by increasing its mass or its weight, or altering some of its other properties. Hence it has been supposed by some that in every process of electrification exactly equal quantities of the two fluids are transferred in opposite directions, so that the total quantity of the two fluids in any body taken together remains always the same. By this new law they contrived to save appearances, forgetting that there would have been no need of the law except to reconcile the two fluids theory with facts, and to prevent it from predicting non-existent phenomena. Theory of one fluid. In the theory of one fluid, everything is the same as in the theory of two fluids, except that, instead of supposing the two substances equal and opposite in all respects, one of them, generally the negative one, has been endowed with the properties and name of ordinary matter, while the other retains the name of the electric fluid. The particles of the fluid are supposed to repel one another, according to the law of the inverse square of the distance, and to attract those of matter according to the same law. Those of matter are supposed to repel each other and attract those of electricity. The attraction, however, between units of the different substances at unit distance is supposed to be very little greater than the repulsion between units of the same kind, so that a unit of matter combined with a unit of electricity will exert a force of attraction on a similar combination at a distance, this force, however, being exceedingly small compared with the force between two uncombined units. This residual force is supposed to account for the attraction of gravitation. Unelectrified bodies are supposed to be charged with as many units of electricity as they contain of ordinary matter. When they contain more electricity or less, they are said to be positively or negatively electrified. This theory does not, like the two-fluid theory, explain too much. It requires us, however, to suppose the mass of the electric fluid so small that no attainable positive or negative electrification has yet perceptibly increased or diminished either the mass or the weight of a body. And it has not yet been able to assign sufficient reasons why the vitreous, rather than the resinous, electrification should be supposed due to an excess of electricity. One objection has sometimes been urged against this theory by men who ought to have reasoned better. It has been said that the doctrine that the particles of matter uncombined with electricity repel one another is in direct antagonism with the well-established fact that every particle of matter attracts every other particle throughout the universe. If the theory of one fluid were true, we should have the heavenly bodies repelling one another. But it is manifest that the heavenly bodies, according to this theory, if they consisted of matter uncombined with electricity, would be in the highest state of negative electrification and would repel each other. We have no reason to believe that they are in such a highly electrified state, or could be maintained in that state. The earth and all the bodies whose attraction has been observed are rather in an unelectrified state, that is, they contain the normal charge of electricity, and the only action between them is the residual force lately mentioned. The artificial manner, however, in which this residual force is introduced is a much more valid objection to the theory. In the present treatise, I propose, at different stages of the investigation, to test the different theories in the light of additional classes of phenomena. For my own part, I look for additional light on the nature of electricity from a study of what takes place in the space intervening between the electrified bodies. Such is the essential character of the mode of investigation pursued by Faraday in his experimental researches. And as we go on, I intend to exhibit the results as developed by Faraday, W. Thomson, and so on, in a connected and mathematical form so that we may perceive what phenomena are explained equally well by all the theories and what phenomena indicate the peculiar difficulties of each theory. Measurement of the force between electrified bodies. Paragraph 38. Forces may be measured in various ways. For instance, one of the bodies may be suspended from one arm of a delicate balance and weights suspended from the other arm till the body, when unelectrified, is in equilibrium. The other body may then be placed at a known distance beneath the first, so that the attraction or repulsion of the bodies when electrified may increase or diminish the apparent weight of the first. The weight which must be added to or taken from the other arm when expressed in dynamical measure will measure the force between the bodies. It is sometimes more convenient to use a torsion balance in which a horizontal arm is suspended by a fine wire or fiber so as to be capable of vibrating about the vertical wire as an axis, and the body is attached to one end of the arm and acted on by the force in the tangential direction so as to turn the arm round the vertical axis and so twist the suspension wire through a certain angle. The torsional rigidity of the wire is found by observing the time of oscillation of the arm, the moment of inertia of the arm being otherwise known, and from the angle of torsion and the torsional rigidity, the force of attraction or repulsion can be deduced. The torsion balance was devised by Maxwell for the determination of the force of gravitation between small bodies, and was used by Cavendish for this purpose. Coulomb, working independently of these philosophers, reinvented it and successfully applied it to discover the laws of electric and magnetic forces. And the torsion balance has ever since been used in all researches where small forces have to be measured. See Article 215. Paragraph 39. Let us suppose that by either of these methods we can measure the force between two electrified bodies. We shall suppose the dimensions of the bodies small compared with the distance between them, so that the result may not be much altered by any inequality of distribution of the electrification on either body. And we shall suppose that both bodies are so suspended in air as to be at a considerable distance from other bodies on which they might induce electrification. It is then found that if the bodies are placed at a fixed distance d, charged respectively with E and E prime of our provisional units of electricity, they will repel each other with a force proportional to the product of E and E prime. If either E or E prime is negative, that is, if one of the charges is vitreous and the other resinous, the force will be attractive, but if both E and E prime are negative, the force is again repulsive. We may suppose the first body A, charged with m units of vitreous and n units of resinous electricity, which may be conceived separately placed within the body, as in experiment 5. Let the second body B be charged with m prime units of positive and n prime units of negative electricity. Then each of the m positive units in A will repel each of the m prime positive units in B with a certain force, say F, making a total effect equal to m prime F. Since the effect of negative electricity is exactly equal and opposite to that of positive electricity, each of the m positive units in A will attract each of the n prime negative units in B with the same force F, making a total effect equal to mn prime F. Similarly, the n negative units in A will attract the m prime positive units in B with a force m prime nf, and will repel the n prime negative units in B with a force nn prime f. The total repulsion will therefore be mm prime plus nn prime f, and the total attraction will be mn prime plus nm prime f. The resultant repulsion will be open bracket mm prime plus nn prime minus mn prime minus nm prime close bracket f, or open bracket m minus n close bracket times open bracket m prime minus n prime close bracket f. Now m minus n equals E is the algebraical value of the charge on A, and m prime minus n prime equals E prime is that of the charge on B, so that the resultant repulsion may be written E prime F, the quantities E and E prime being always understood to be taken with their proper signs. Variation of the force with the distance. Paragraph 40. Having established the law of force at a fixed distance, we may measure the force between bodies charged in a constant manner and placed at different distances. It is found by direct measurement that the force, whether of attraction or repulsion, varies inversely as the square of the distance. So that if F is the repulsion between two units at unit distance, the repulsion at distance r will be F over r squared, and the general expression for the repulsion between E units and E prime units at distance r will be E prime F over r squared. Definition of the electrostatic unit of electricity. Paragraph 41. We have hitherto used a wholly arbitrary standard for our unit of electricity, namely, the electrification of a certain piece of glass as it happened to be electrified at the commencement of our experiments. We are now able to select a unit on a definite principle, and in order that this unit may belong to a general system, we define it so that F may be unity. Or in other words, the electrostatic unit of electricity is that quantity of electricity which, when placed at unit distance from an equal quantity, repels it with unit of force. This unit is called the electrostatic unit to distinguish it from the electromagnetic unit, to be afterwards defined. We may now write the general law of electrical action in the simple form F equals E prime r to the power minus 2. Dimensions of the electrostatic unit of quantity. Paragraph 42. If Q is the concrete electrostatic unit of quantity itself, and E the numerical values of particular quantities, if L is the unit of length, and R the numerical value of the distance, and if F is the unit of force, and F the numerical value of the force, then the equation becomes F open bracket L F to the minus 1 close bracket equals E prime r to the minus 2, quantity Q squared L to the minus 2, whence quantity Q equals L to the 3/2 F to the 1/2, which is L to the 3/2 times T to the minus 1 times M to the 1/2. This unit is called the electrostatic unit of electricity. Other units may be employed for practical purposes and in other departments of electrical science, but in the equations of electrostatics, quantities of electricity are understood to be estimated in electrostatic units. Just as in physical astronomy, we employ a unit of mass which is founded on the phenomena of gravitation and which differs from the units of mass in common use. Proof of the law of electrical force. Paragraph 43. The experiments of Coulomb with the torsion balance may be considered to have established the law of force with a certain approximation to accuracy. Experiments of this kind, however, are rendered difficult and in some degree uncertain by several disturbing causes, which must be carefully traced and corrected for. In the first place, the two electrified bodies must be of sensible dimensions relative to the distance between them in order to be capable of carrying charges sufficient to produce measurable forces. The action of each body will then produce an effect on the distribution of electricity on the other, so that the charge cannot be considered as evenly distributed over the surface or collected at the center of gravity. But its effect must be calculated by an intricate investigation. This, however, has been done as regards two spheres by Poisson in an extremely able manner, and the investigation has been greatly simplified by Sir William Thomson in his theory of electrical images. See articles 172 to 174. Another difficulty arises from the action of the instrument by induction on the sides of the case containing the instrument. By making the inside of the instrument accurately cylindric and making its inner surface of metal, this effect can be rendered definite and measurable. An independent difficulty arises from the imperfect insulation of the bodies, on account of which the charge continually decreases. Coulomb investigated the law of dissipation and made corrections for it in his experiments. The methods of insulating charged conductors and of measuring electrical effects have been greatly improved since the time of Coulomb, particularly by Sir William Thomson. But the perfect accuracy of Coulomb's law of force is established not by any direct experiments and measurements, which may be used as illustrations of the law, but by a mathematical consideration of the phenomenon described as experiment 7. Namely, that an electrified conductor B, if made to touch the inside of a hollow closed conductor C, and then withdrawn without touching C, is perfectly discharged, in whatever manner the outside of C may be electrified. By means of delicate electroscopes, it is easy to show that no electricity remains on B after the operation, and by the mathematical theory given at Article 74, this can only be the case if the force varies inversely as the square of the distance, for if the law had been of any different form, B would have been electrified. The electric field. Paragraph 44. The electric field is the portion of space in the neighborhood of electrified bodies considered with reference to electric phenomena. It may be occupied by air or other bodies, or it may be a so-called vacuum, from which we have withdrawn every substance which we can act upon with the means at our disposal. If an electrified body be placed at any part of the electric field, it will be acted on by a force which will depend, in general, on the shape of the body and on its charge. If the body is so highly charged as to produce a sensible disturbance in the previous electrification of the other bodies. But if the body is very small, and its charge also very small, the electrification of the other bodies will not be sensibly disturbed, and we may consider the body as indicating by its center of gravity a certain point of the field. The force acting on the body will then be proportional to its charge, and will be reversed when the charge is reversed. Let E be the charge of the body, and F the force acting on the body in a certain direction. Then when E is very small, F is proportional to E, or F equals R times E, where R is a quantity depending on the other bodies in the field. If the charge E could be made equal to unity without disturbing the electrification of the other bodies, we should have F equals R. We shall call R the resultant electric force at the given point of the field. Electric potential. Paragraph 45. If the small body carrying the small charge E be moved from the given point to an indefinite distance from the electrified bodies, it will experience at each point of its course a force RE, where R varies from point to point of the course. Let the whole work done on the body by these electrical forces be VE, then V is the potential at the point of the field from which the body started. If the charge E could be made equal to unity without disturbing the electrification of other bodies, we might define the potential at any point as the work done on a body charged with unit of electricity in moving from that point to an infinite distance. A body electrified positively tends to move from places of greater positive potential to places of smaller positive or of negative potential. And a body negatively electrified tends to move in the opposite direction. In a conductor, the electrification is distributed exactly as if it were free to move in the conductor according to the same law. If therefore two parts of a conductor have different potentials, positive electricity will move from the part having greater potential to the part having less potential as long as that difference continues. A conductor therefore cannot be in electrical equilibrium unless every point in it has the same potential. This potential is called the potential of the conductor. Equipotential surfaces. Paragraph 46. If a surface described or supposed to be described in the electric field is such that the electric potential is the same at every point of the surface, it is called an equipotential surface. An electrified point constrained to rest upon such a surface will have no tendency to move from one part of the surface to another, since the potential is the same at every point. An equipotential surface is therefore a surface of no electrical force, or a level surface. The resultant force at any point of the surface is in the direction of the normal to the surface, and the magnitude of the force is such that the work done on an electrical unit in passing from the surface V to the surface V prime is V minus V prime. No two equipotential surfaces having different potentials can meet one another, because the same point cannot have more than one potential. But one equipotential surface may intersect itself, and this takes place at all points and lines of equilibrium. The surface of a conductor in electrical equilibrium is necessarily an equipotential surface. If the electrification of the conductor is positive over the whole surface, then the potential will diminish as we move away from the surface on every side, and the conductor will be surrounded by a series of surfaces of lower potential. But if, owing to the action of external electrified bodies, some regions of the conductor are electrified positively and others negatively, the complete equipotential surface will consist of the surface of the conductor itself together with a system of other surfaces, meeting the surface of the conductor in the lines which divide the positive from the negative regions. These lines will be lines of equilibrium, so that an electrified point placed on one of these lines will experience no force in any direction. When the surface of a conductor is electrified positively in some parts and negatively in others, there must be some other electrified body in the field besides itself. For if we allow a positively electrified point, starting from a positively electrified part of the surface, to move always in the direction of the resultant force upon it, the potential at the point will continually diminish till the point reaches either a negatively electrified surface at a potential less than that of the first conductor, or moves off to an infinite distance. Since the potential at an infinite distance is zero, the latter case can only occur when the potential of the conductor is positive. In the same way, a negatively electrified point moving off from a negatively electrified part of the surface must either reach a positively electrified surface or pass off to infinity, and the latter case can only happen when the potential of the conductor is negative. Therefore, if both positive and negative electrification exist on a conductor, there must be some other body in the field whose potential has the same sign as that of one conductor but a greater numerical value. And if a conductor of any form is alone in the field, the potential of every part is of the same sign as the potential of the conductor. Lines of force. Paragraph 47. The line described by a point moving always in the direction of the resultant force is called a line of force. It cuts the equipotential surfaces at right angles. The properties of lines of force will be more fully explained afterwards, because Faraday has expressed many of the laws of electrical action in terms of his conception of lines of force drawn in the electric field and indicating both the direction and the magnitude of the force at every point. Electric tension. Paragraph 48. Since the surface of a conductor is an equipotential surface, the resultant force is normal to the surface, and it will be shown in Article 78 that it is proportional to the superficial density of the electrification. Hence, the electricity on any small area of the surface will be acted on by a force tending from the conductor and proportional to the product of the resultant force and the density, that is, proportional to the square of the resultant force. This force, which acts outwards as a tension on every part of the conductor, will be called electric tension. It is measured like ordinary mechanical tension by the force exerted on unit of area. The word tension has been used by electricians in several vague senses, and it has been attempted to adopt it in mathematical language as a synonym for potential. But on examining the cases in which the word has been used, I think it will be more consistent with usage and with mechanical analogy to understand by tension a pulling force of so many pounds per square inch exerted on the surface of a conductor or elsewhere. We shall find that the conception of Faraday that this electric tension exists not only at the electrified surface, but all along the lines of force, leads to a theory of electric action as a phenomenon of stress in a medium. Electromotive force. Paragraph 49. When two conductors at different potentials are connected by a thin conducting wire, the tendency of electricity to flow along the wire is measured by the difference of the potentials of the two bodies. The difference of potentials between two conductors or 2 points is therefore called the electromotive force between them. This name is used for many other causes that influence the motion of electricity, but these causes are not considered in treating of statical electricity. We shall consider them when we come to chemical actions, motions of magnets, inequalities of temperature, and so on. Capacity of a conductor. Paragraph 50. If one conductor is insulated while all the surrounding conductors are kept at the zero potential by being put in communication with the earth, and if the conductor, when charged with a quantity E of electricity, has a potential V, the ratio of E to V is called the capacity of the conductor. If the conductor is completely enclosed within a conducting vessel without touching it, then the charge on the inner conductor will be equal and opposite to the charge on the inner surface of the outer conductor, and will be equal to the capacity of the inner conductor multiplied by the difference of the potentials of the two conductors. Electric accumulators, a system consisting of two conductors whose opposed surfaces are separated from each other by a thin stratum of an insulating medium, is called an electric accumulator. Its capacity is directly proportional to the area of the opposed surfaces and inversely proportional to the thickness of the stratum between them. A Leyden jar is an accumulator in which glass is the insulating medium. Accumulators are sometimes called condensers, but I prefer to restrict the term condenser to an instrument which is used not to hold electricity, but to increase its superficial density.